Hello, my name is John Schuster, and I'm Terabeam's Chief Technical Officer, and I'd like to make a presentation for you today to discuss our free space optics and millimeter wave technology. I think the first thing I'd like to address is why we've developed these technologies. At this time, when you look at the networks that cross the world, the connections between cities are at data rates of 2.5 gigabits per second and higher, whereas the connections in our buildings that actually connect our computers are also at 100 megabits per second and even multiple gigabits per second. Unfortunately, the connection between these wide area connections and the office connections is typically a lot slower, maybe only a couple megabits per second or less than 1%. With our technologies of free space optics and millimeter wave, we actually have the ability of making those connections seamless. We're having the same data rates fully across the wide networks and the local business networks. I guess one of the primary questions you might ask is, why not just bury more fiber? And the reason for that is purely cost. Fiber takes time, and takes rights of way and permits and trenching, and all of that really translates into cost. By doing it wirelessly, we can skip most of the rights of ways and permit side, as well as the trenching, and also save a lot of time. And therefore, comes down almost exclusively to cost, that FSO and millimeter wave allow you to deploy connectivity where it may just never make sense to deploy fiber. In order to really understand these technologies, it's a good idea to start with how fiber optic cable works. Fiber optic cable is quite literally strands of glass, with one being an input direction to a computer and a separate strand being the output direction from the computer. Information is transmitted on these strands of glass, with light on being a 1 and light off being a 0. Today, fiber optic is capable of transmitting data at speeds as high as 40 gigabits per second in pretty routine operation. And this is the equivalent of transmitting more than 7 CDs every second of operation. In the future, you're going to see data rates even higher than this, with multiple hundreds of gigabits per second possible on single strands of fiber. And we expect this trend to keep continuing as technology advances and the demand for bandwidth increases. Where FSO compares to fiber optic is quite literally, it is fiber through the air. Fundamentally, anything you can do on fiber optic, you can do in free space optics. And the way it works is that data is entered into a computer network and is connected to the free space optics transmitter, as shown here is point 2. The point 2 transmitter takes that information and creates a beam of light that is transmitted across free space and received at the opposite end, where it is converted back into the appropriate format for the required network. The opposite direction is basically exactly the same and happens simultaneously, so that in free space we literally have the equivalent to 2 strands of glass going in opposite directions. But there is no glass, it is only the air in between. Millimeter wave is very similar to free space optics, except instead of pulses of light, we use pulses of radio frequency energy. To be considered millimeter wave, the frequencies must be between 30 and 300 gigahertz, corresponding to wavelengths of approximately 1 millimeter up to about 1 centimeter. When you look at this slide, you can see that it's very similar to an FSO, is that there's a transmit and a receiver, both operating in transmit and receive modes, so that you have a full duplex link as shown before, except, once again, instead of light, we're using pulsed radio energy. The core value proposition behind these technologies is that they allow very close spacing of links with little or no interference. Traditional wireless systems tend to broadcast energy quite widely, and the result is if they're positioned too close together, interference will occur. In addition, both of these technologies transmit very narrow beams of energy. That a typical system will have a beam diameter of less than 5 meters at a kilometer. And with that type of beam spread, the systems are inherently very secure. In addition, from the US standpoint, both of these technologies are unlicensed everywhere. They can be used for any type of deployment, both residential and commercial and carrier class. And that is a unique feature that most RF technologies cannot support. In addition, when you look from a worldwide standpoint, FSO is unlicensed everywhere. And that allows us to build the same system for every market around the world. And that is also quite unique. Millimeter wave is not quite as flexible in the fact that only Japan, Canada, and the United States have really fully defined spectrum allocations at these frequencies. But we expect the rest of the world to follow quite soon, and we will continue to introduce products in those countries as spectrum becomes available. Another goal with these technologies is that they be easy to install. That is a value proposition, but must be part of the engineering that goes into each system. When you're projecting such narrow beams of energy, alignment and installation can be quite tricky. And our goal in our designs is to make it relatively simple. FSO is particularly good for behind window deployments, and that's because the optical energy penetrates windows very much like light from sun does. Millimeter wave is more typically a rooftop installation technology, and that's because window glass can tend to reflect the energy a little more unpredictably. That being said, some behind window deployments are perfectly viable with millimeter wave. And furthermore, most rooftop deployments are also perfectly valid with FSO. And it really comes down to which technology best serves your needs. In both cases, neither technology requires trenching or permits, and both offer fiber optic-like data rates. We currently offer systems in the FSO domain offering data rates from 125 to 155 megabits per second, and we expect to be offering higher data rate systems in the not-too-distant future. Currently in the millimeter wave domain, we offer systems at 125, 155, 622, 1.25 gigabits per second, and 1.42 gigabits per second, quite literally fiber optic data rates. And once again, as we look into the future, higher data rates are very possible. I personally believe we will be offering a 10 gigabit per second solution within the next 3 years. The only challenge there is when does the market need it? Another core opportunity with both of these technologies is they're relatively easy to redeploy. Fiber optic is a stranded expense. Once it's in the ground, you can't take it with you. When both of these technologies, FSO and millimeter wave, can be moved if the customer moves or if you no longer need the connectivity at that location. This slide shows you some of the applications for wireless broadband. Point 1 shows single customer access, where from a single office facility, millimeter wave and FSO can be used to tie individual end users into that point, essentially expanding the footprint of the building from a network standpoint. Both of these technologies can also be used in point-to-point connections, as shown in bullet 2. They can be used back to back to back almost indefinitely in a daisy chain fashion, so that you can quite literally build wireless rings with these technologies. They are ideal in a campus connection situation where you just want to connect the network in one building to the network in another building, so you do not have to necessarily rent wires or copper or fiber optic from the local phone company. It's great for diverse laterals, as shown in 4. And in this case, using FSO and millimeter wave as an alternative connection to whether it be fiber or copper. And that can be multiple forms of that. FSO and millimeter wave can be the primary connection and use the copper as the backup. Alternatively, use it the other way with fiber as the primary and FSO and millimeter wave as the backup. It really is up to the user to decide. And in these days of ever increasing security and the challenges faced when a network fails, diverse lateral is a major use of these technologies. Point 5 shows a backhaul or ring closure application, where most networks like to have full ring architectures, because if one portion of that ring fails, it's still possible to get to every point on the network by going the opposite direction around the ring. In many areas, however, it may be quite difficult to close some portion of the ring because of the unavailability of fiber or for cost reasons, for instance. And millimeter wave and FSO, by offering fiber optic-like data rates, can be used to close that connection seamlessly. And the last point shown here is the multi-tenant building application. And in that role, if you have a fiber optic deployment, for instance, and you want to connect buildings to that fiber optic ring, the additional fiber to tie those together may be very cost prohibitive. And you can use millimeter wave and FSO for that final connection to actually leverage the cost and capability of your existing fiber asset. I've already talked quite a bit about FSO and millimeter wave wavelengths. As shown on this chart, FSO operates, I should say Terabeam FSO operates in the wavelength of 1550 nanometer. FSO as an industry tends to operate at frequencies or wavelengths from 785 nanometer all the way through 10,000 nanometer, which is also defined as 10 micron. The selection of which wavelength makes the most sense comes down to many different choices. 785 to 850 nanometer components are based upon silicon technology and are classic of CD players and CCD cameras. And the result is the components are very low cost. But the challenges are they are also not typically telecom grade. And as Terabeam, we believe that we require carrier grade components for our market opportunity. And as a result, we do not use a lot of 785 technology today. That being said, in the future, we are very likely to introduce such systems for lower cost applications. 1550 nanometer, shown in the center here, is the frequency that we choose to use, or I should say wavelength we choose to use on all of our systems today. And the reason for that is because of the greater eye safety that 1550 allows. For the same eye safety classification, we can transmit between 50 and 65 times as much power at 1550 as we can at 785 or 850. And the reason for that is the way the human eye works, and we'll get into that a little more on a later slide. In addition, 1550 is quite interesting because it is less susceptible from interference by the sun. And when we're transmitting these beams of light across the sky, we do worry about solar interference. And the reason that we have less of a challenge at 1550 is because the sun just doesn't have as much spectral content at that wavelength. It tends to have a lot more at 785, 850, and that is supported by the visible spectrum where the human eye works from 400 to 700. 785 is just slightly beyond visible, and as a result, that is why the human eye has been optimized for the 400 to 700 nanometer frequency, because that is where the sun is most intense. In addition, 1550 is ideal because it is based on the high reliability long-haul fiber technology. It is exactly the same wavelength that is used to connect these cities around the world. And we are able to leverage the laser developments, detector developments, etc. to reduce cost. It is still not an inexpensive technology, but it is ideal from a reliability and a future technological growth perspective. Using this wavelength, Terabeam has actually demonstrated connections above 160 gigabits per second in the laboratory environment. We're not offering products of that capability today, but sticking to this wavelength allows us to have that future potential. And then lastly, I'd like to talk a little bit more about millimeter wave. As I mentioned, that is defined as the region between 30 gigahertz and 300 gigahertz. In general, millimeter wave components are slightly less expensive than optical components. And where optical, we tend to worry about things that block light, such as fog. Millimeter wave, we tend to worry about things like rain, which tend to interfere with radio signals. That being said, it penetrates fog wonderfully well. And there are some trade-offs there depending upon where you live and where the link is being installed. When you talk about wireless, it's very important to talk about modulation schemes. And that is specifically how the information is encoded upon the energy that is transmitted. As I mentioned before, in free space optics and in fiber, light on is a 1, light off is a 0. Whereas in millimeter wave, the modulation scheme is slightly different. Its energy on is a 1 and energy off is a 0. And to first order, they're very similar, but when you actually get into a little detail, there are some slight differences. We refer to our FSO modulation scheme as on-off keying, and we refer to our millimeter wave modulation scheme as direct digital modulation. Those are industry standard designations, and we can't claim to have invented them, but we do claim to have optimized them a little bit. Another concept I'd like to start discussing is of divergence, and that is how a beam spreads as it propagates through the atmosphere. Typically, when you think of a radio, it is projecting a beam or a sphere of energy that is radiating from a starting point and goes in all directions simultaneously. But with FSO and millimeter wave, we use antennas, whether they be a telescope, which is one type of antenna in the optical domain, or using a classic parabolic antenna to focus the radio emissions, that can help us focus this energy so it doesn't spread everywhere simultaneously. That being said, we do want to diverge it a little bit. We don't want the energy to be perfectly collimated or a perfectly uniform cylinder of light or radio energy never changing. We want it to spread a little bit because it helps the system stay aligned and compensate for slight changes in alignment due to vibration. The way to think about this is that if you had a laser pointer and were trying to illuminate something on the other side of the room, you'd have to hold your hand very steady. Whereas if you were using a flashlight, it would be actually okay to move around a little bit. And the same exact thing applies to both of these technologies. We want to spread it just a little bit so it's a little easier to maintain on target. As we discussed divergence, the core unit of measure is a milliradian. And a milliradian is 1/17 of a degree. And that's not a common unit of measure in the angular space for most of the world, but in this particular realm, it's what we use. In general, the greater the divergence, the weaker the signal at the receiver. So we do want to spread the beam enough to make sure it's easy to stay aligned, but we want to keep it as focused as much as possible to maximize energy at the receiver and maximize link performance. And this is a continuous trade that you will see throughout Terabeam systems, where some are designed with advanced pointing and tracking in very narrow beams, and other systems are using relatively large beams but are lower cost because they don't have the pointing and tracking. Part of understanding how a system works is understanding what the spot size or beam diameter will be at a given range. And a quick order of magnitude way to think about this is just multiplying the angle in milliradians times the range in kilometers results in the spot size in meters. Now this is very much small angle approximation calculations, but it's very valid for the narrow beams we use. What this translates into is when we say a beam has a half milliradian divergence, it means it will spread to a diameter of about half a meter at a distance of a kilometer. A 1.6 milliradian beam will spread to a diameter of about 1.6 meters at a kilometer. And lastly, 1 degree at 1 kilometer is about 17 meters because it's 17 milliradians. The next concept I'd like to introduce you to is field of view. And this is a slightly more complex concept to understand. When we talk about free space optics in particular, we talk about the cone of light it projects. But the receive optical system, or optical antenna if you will, has exactly the same kind of cone of reception, that is its field of view. And essentially, if light that is aimed at that receiver does not originate within that cone, it will never impact the receiver and it will never be seen. This adds to the security of the systems because it makes it interfering with them virtually impossible. That essentially, for another unit to interfere with an operational link, it has to be placed right next to the other side of the link, which will be very apparent to whoever's using or operating the system. In addition, a small field of view helps with resistance to interference from the sun, because if it only detects light within a small region, the sun must locate within that small region. This can be a challenge with rooftop-mounted systems, for instance, when the sun will set behind a unit. But typically, if you're mounted further down on a building or behind a window, it's highly unlikely that the sun will be able to interfere with the system. Kind of a second or third order characteristic that is important to field of view is that high data rate detectors, and we define high data rate as being hundreds of megabits and multiple gigabits per second, typically have very small field of views through their optical system. And this makes pointing and tracking just as important from making sure the receiver stays aligned as it is from making sure the transmit power stays aligned. Another concept that you will hear very frequently while talking about these technologies is the attenuation in power levels expressed in terms of dB. dB can be a rather scary concept if you don't use it often. Really, all it is a way of expressing the relative ratio between two signal powers. And this particular slide shows you the actual equation. Personally, I never punch the math. I tend to use the rules of thumb because it's much easier for me. All you really need to know is that a change in 2 in power is 3 dB, a change of 4 is 6 dB, a change of 8 is 9 dB, and a change in 10 is 10 dB. And if you really just remember factors of 2 is 3 dB and factors of 10 is 10 dB, you can get just about anywhere. As another example of this, is example 2 on this slide, is the difference between 1,000 milliwatts and 1 milliwatt is essentially 3 factors of 10, or 30 dB. We use it because this allows for relatively simple mathematics to express rather complicated relationships, and is quite common in the optical and RF world. For both of these technologies, it's very important to understand the environmental factors. And when we say environmental factors, these are the things that Mother Nature throws at us that can affect performance of the systems. And these are diverse as building motion on low clouds, to things like cranes, which aren't exactly Mother Nature creations, but have very similar effects, fog, scintillation, rain, and oxygen absorption, or just the content of the atmosphere itself, which affect the performance of the systems. First one we'll talk about in some detail is solar interference. And solar interference is the direct or reflected sunlight that can interfere with the data or tracking sensors on an FSO system. Solar interference does not impact millimeter wave at all. In general, solar interference has to be worried about from east-west links, and really isn't a factor on north-south links, but it is something that should be taken into account. Typically, when an allergy does result or is caused by sunlight, it will be on the order of a few minutes, a few days a year, and that has to do with how the sun processes around the Earth throughout the year as the orbit of the Earth goes around the sun. From a performance standpoint, 1550 nanometer systems are much more immune to this. And that is once again because there is less solar energy at 1550 nanometer than there is at lower or shorter wavelengths such as 785 to 850. Another thing to keep in mind is that both FSO and millimeter wave, with their very narrow beams, are true line-of-sight technologies. You have to be able to see the other side of the link from where the primary side of the link or the link you're standing on is located. If you can't see it, or if it gets blocked, it's just not going to work. And this particular slide shows you some of the obstructions we've managed to find in our several years messing with these two technologies. Everything from cruise ships to cranes to even a shot of an airplane's landing gear. Typically a more common obstruction is actually the window washer. Now both of these systems are very safe and are in no way going to result in injury to a window washer, and as we'll explain a little more later, some details. But that's a core thing to remember with Terabeam systems. They are safe for all environmental installations. When you talk about both FSO and millimeter wave technologies, it's very important to understand how the atmosphere and the things in the atmosphere will attenuate the performance of the systems. This particular slide shows you the various characteristics and how each technology is impacted by the relative causes. This slide shows that drizzle in green relative to excessive rain in dark blue, relative to fog shown in yellow, and the orange line which shows the molecular absorption characteristics of the atmosphere and how they all overlay. For millimeter wave shown on the left-hand side, oxygen absorption in the pure atmosphere is the primary limiter in performance. Oxygen absorbs this frequency at a rate of 16 dB per kilometer. And as I explained earlier, that's 1 factor of 10 and 2 factors of 2, which is the equivalent of a reduction in 40 for every kilometer that the signal travels. The one other limitation with millimeter wave is shown here is that truly excessive rain will impact system performance. So that when looking at the availability or what weather events a system must work in, excessive rain is the limiting factor that must be taken into account. FSO, more on the right-hand side, which we're showing is operating in frequencies from 30 to 400 terahertz, the primary driver is fog. That was represented that the yellow line is far higher than the molecular absorption or even the excessive rain. A unique opportunity shown by this particular slide is that if you actually use both technologies side by side with FSO for the heavy rain conditions and millimeter wave for the heavy fog conditions, you can actually overcome virtually everything because the two conditions don't happen at the same time. Talk a little bit oxygen absorption. Oxygen absorption is shown on the previous slide right at that peak at 60 gigahertz. And it rolls off quite a bit as you go below 60 gigahertz and you go above 60 gigahertz. But right on peak, it's 16 dB per kilometer and represents a 98% attenuation for every kilometer traversed by the signal. With today's power limits as established by the FCC, this results in a maximum practical range for these systems of about 1.4 kilometers. Basically, beyond that, there's not enough signal for the systems to operate at all. Now, this may appear as a limit, but the same oxygen absorption allows for very dense deployments because you can deploy links over and over again in close proximity. And it also allows for very high security because much past that 1.4 kilometers, there's no energy to intercept. Rain and snow, in a little more detail, are also attenuators as discussed a little bit earlier. Millimeter wave is attenuated by heavy rain. This adds to the oxygen absorption, but when we spec a system and its performance, we tend to take oxygen absorption into account as part of just that's the way it is. Heavy rain is very dependent upon where you are on the planet, and if you were deploying here in Seattle, where it very rarely rains heavy, it actually works extremely well. Whereas if you're deploying in, say Singapore, where heavy rain is a pretty regular occurrence, the ranges will be much shorter for the same level of availability or performance. FSO, on the other hand, really is not significantly attenuated by rain. I actually should clarify that a little bit. FSO is attenuated so heavily by fog that the rain input is typically not very important. In reality, it is attenuated, but once again, if you deployed with fog as your limiting characteristic, rain will almost never be a problem. The only exceptions to this are, once again, countries such as Singapore, where fog is quite rare and heavy rain is the predominant weather effect. That is an area where rain will be the limiter in deployment. Heavy snow typically really doesn't affect either FSO or millimeter wave by itself. If you think of the way the human eye works, you see quite well in snow, and you tend to see quite well in heavy rain. And FSO performs very similarly in those conditions. The only exception to this is whiteout conditions, and that will take an FSO link down. It will not take a millimeter wave link down. So it's, once again, what is the predominant climate where you're going to install may depend on what system is the appropriate selection for you. As we talked fog just a little bit on and off, this slide brings it into a little more focus. Fog is a problem for FSO. There is no escaping from it. It is directly due to the absorption and scattering of the optical signals due to the particles of fog. The real challenge here is that fog particles happen to be just about the same size of the wavelength of light. As a result, they scatter extremely effectively. To put this in a little bit of perspective, we've talked about oxygen absorption introducing 16 dB per kilometer of attenuation at 60 gigahertz millimeter wave. We, Terabeam, have measured fog events in excess of 300 dB per kilometer. That is a huge number for any wireless system to compensate for, and that is why typically FSO systems will be deployed at short range for high availabilities. As a general rule of thumb, an FSO system will work 2 to 3 times further than the human eye can see. Meaning if you can even see the shadow of the opposite end of the link, and convince yourself that there's a building there, the system will be working fine. If you're not even sure there is an opposite end of the link, that is when there will be problems. The next challenge I'd like to talk about is scintillation. And this is a slightly more complex atmospheric effect. And the best example of it is the mirage effect when you look down a hot road and you see the shimmer, or even the shimmer of light passing through, for instance, the exhaust of a car, or even the twinkle of a star. All of those are scintillation effects. And the result of this is that the atmosphere is really just pockets of air of varying temperature, pressure, and index of refraction. And it really is the same effect as a collection of lenses floating around, always changing position. And heat radiating from surfaces like asphalt causes the air to move around and thereby causes these lenses to move around. Each of these lenses slightly grabs the optical beam passing through it and can steer it around. And the result of this is that if you actually had the ability to image an FSO beam at the end of a link, it would look very much like a beam of light passing through the bottom of a swimming pool. That there's going to be dark spots and there's bright spots and they're continuously moving. Typically, scintillation does not result in an outage. It just results in increased error rate. And that's because there will be some periodic statistical chance that all those lenses will stack up in such a way that it'll steer all the light off your receiver. And for that moment of time, there won't be enough energy on the system for it to operate at zero errors. But the next millisecond, those particular lenses will have moved around and the system will be back to operating normally. Scintillation is a bigger challenge on hot days at relatively long ranges. It is also a limitation if the beam is skimming a hot surface. For instance, a black roof or even the edge of a wall around the building. Those surfaces can get hot enough in the sun that they will create air currents and thereby promote scintillation. In general, scintillation can be compensated for with proper installation, but it is something that has to be thought about. Fundamentally, it really is not a factor for millimeter wave and should also be kept in mind. When installing FSO and millimeter wave, one of the fundamental limitations is range loss. And range loss is really how the energy spreads out as the beam propagates over distance. As we talked about divergence earlier, that a 1 milliradian beam has a diameter of a meter at a kilometer. When you go to 2 kilometers, it's now 2 meters. So you've essentially doubled the size of the circle. And every time you double the size, you take a 6 dB hit in available energy in a particular area. As this chart shows, for instance, going from 250 meters to 500 meters is a 10 dB change in range losses. Going from 500 meters to 1,000 meters is about another 5 dB loss. Now the reason this isn't 6 dB is because the energy transmitted from these systems is not perfectly uniform. It actually has a distribution that is Gaussian in shape, meaning that there is slightly more energy at the center than there is at the edges, and that is why it's not a perfectly uniform change as range increases. But still looking at elliptica going from 1,000 to 2,000 meters, once again it's another 6 dB. For the millimeter wave, or gigalink parabola as shown here, the same factors apply, that 250 to 500 meters is 26 to minus 32 dB, or once again a factor of 6. It should be said that these range losses are independent of the oxygen absorption losses, and they would have to be added to this for actual link budget calculations. When installing equipment behind windows, it's very important to take into account how the window will attenuate the signal. A typical clear sheet of glass reflects about 4% of the light that impacts it per surface. For a single pane clear sheet, it's on the order of a 1 dB of attenuation. That being said, if you have a tinted window, especially those with a low E coating or low emissivity coating designed to block infrared radiation, the attenuation can be more than 20 or 30 dB through a single window. And the result of that is that something that looks clear to the human eye may be completely inappropriate for the FSO system you'd like to install behind it. Terabeam has developed a window attenuation meter, which is a device that will allow you to measure the window attenuation from inside the building by looking at the reflection off of each surface. This is an important part of understanding how a system will work, because the human eye just is not a very good meter for determining what a window will actually do at optical wavelengths where our systems operate. From a millimeter wave perspective, window attenuation is a little different. A metal coating typically is conductive, and that can impact millimeter wave transmission, but is much harder to measure. In addition, multi-pane glass can have unique effects on millimeter wave transmission, and that's because the cavity between the two panes of glass is very close to the wavelength of the energy being transmitted. And that at certain points where that distance will become a tuned cavity relative to the angle of the energy going through it, you can actually end up with extremely high millimeter wave attenuations. That being said, there are times when it will work extremely well. It's just hard to predict. So keep that in mind if you want to do an indoor millimeter wave installation. We don't recommend it, but it can be done if the appropriate engineering care is taken into account and understanding of the risks is also planned for. As I mentioned earlier, a plain sheet of glass will reflect 4% of the light that impacts it just because of the change between air and glass. If you approach a piece of glass at a higher angle with the beam of light, that reflection will increase as shown by the graph on this slide. Approaching a 90-degree angle, the reflectance is approaching 100%. So that when installing an FSO system behind a window, it's best to keep the angles at 45 degrees or less. It is possible to install at angles substantially higher than this, but it is not recommended as there will be substantial attenuation going through the window. The next challenge that is very important to keep track of is building motion. As mentioned, both FSO and millimeter wave transmit relatively narrow divergence beams and have narrow fields of view. And as we talked about with the laser pointer, holding it on target all the way across the room, if the building twists due to thermal expansion or wind, it will steer that alignment and the system will go down. Typically, the largest source of motion is thermal expansion causing the building to tip up and tilt down as the sun goes from one side of the building to the other side across the day. Wind sway tends to be slightly less in magnitude but more frequent in occasion. And vibration, such as people walking or heating, ventilation, and air conditioning equipment, has a very low magnitude but happens many times per second. And that an appropriate installation, each of these characteristics is going to have to be understood and taken into account. In general, we have designed Terabeam equipment to operate in virtually any of these conditions flawlessly, but there will be extreme cases of vibration or particularly moving mobile structures, for instance, where it may not be possible to maintain alignment in worst-case conditions. A particular example of this would be a wooden pole on a windy day that may move more than we've allowed based upon traditional buildings, and it should be kept in mind. This slide shows in a cartoon-type fashion really what this motion looks like from a millimeter wave and FSO system. On the left-hand side of the slide, you see a FSO system with pointing and tracking perfectly compensating for the building motion. And it should be understood, pointing and tracking is compensating for motion in the building to which you are mounted. It is not compensating for motion on the opposite side of the link. That being said, it will compensate for that motion, but conceptually it should really be thought of compensating for the mounting location where the system sits. Ideally, the FSO system would stand perfectly still as the building moved around it. As you can also see on the left, the system without pointing and tracking, which is the blue circles or blue cone, is incapable of maintaining alignment as the building tips up and tips down. And that is the whole goal of pointing and tracking, to compensate for that motion at all times. All in all, each of the factors we've just talked about impacts link availability. And link availability is the percentage of time that the system will be operational. Typically in the telecom world, we speak of things as having a 5 nines availability, which means the downtime of less than 5 minutes per year. In my experience, the world talks about 5 nines availability and even claims 5 nines availability, but very rarely actually delivers it. I know my cell phone isn't close to 5 nines. I know my cable modem at home isn't close to 5 nines. A single string of fiber isn't close to 5 nines. That being said, it is the goal we all strive for. Typically, an FSO system can be pretty easily deployed with a 3 nines availability, meaning that it'll be down 0.1% of the time, or about 8.75 hours per year. The limitation there is once again the occurrence of fog that will take a system down. FSO can be deployed at availabilities higher than 3 nines, but typically only at very short ranges and to allow for the worst case fog conditions. Millimeter wave, on the other hand, is fully capable of 4 nines or 5 nines deployments at really quite good ranges compared to FSO. And I don't want to say that one technology is better than another. It really depends on what you need your application or what is required. FSO may be limited to 3 nines in a best case installation, but it is also capable of working at very long ranges at lower availability, whereas millimeter wave tends to be limited by the oxygen absorption to short ranges of approximately 1.4 kilometers. The Elliptica FSO system can operate at over 4 kilometers in clear air, even though the availability will be quite low for weather events. So that must be taken into account when an application is being examined. Part of planning an installation is calculating what the link availability will be. And that is typically 3 steps. The first step being calculating the amount of margin the system will have in clear air, which is where dB tends to appear. Calculating the probability of attenuation, whether it be fog or rain, and then determining how often those weather characteristics will occur based upon long-term weather statistics. So what is clear air link margin? Well, clear air link margin is defined as the difference between the optical power or millimeter wave power received in clear air versus the minimum power level required for a given air rate. Alternatively, it can be thought of as the amount of power available to punch through weather. As we mentioned earlier, 30 dB of margin means that only 1 part in 1,000 of the energy transmitted actually has to get to the receiver for the system to work. 50 dB of margin means 1 part in 100,000 must get there. And to think about this in a slightly different manner, with an FSO system, if you took a piece of cardboard and put it over the front of the aperture and poked a hole that was only 1/100,000th of the area of the aperture, if we had 50 dB of margin on that link, the link will still operate with 0 errors. And another way that this can be thought about is that if the window gets dirty, you have to block all but 100,000th of it in order for the system to go down. That's why we really don't worry about dust. Typically, we express clear air link margin at an error rate of 10 to the minus 9, which means 1 error for every billion bits transmitted. For certain applications, you may want to look at an error rate of 10 to the minus 12, but that typically only results in about a 1 dB change in available margin and is quite an easy conversion. We typically express link margin in terms of a link budget. And a link budget is really no different than a financial budget in that you start with so many dollars or so much energy, and then it gets consumed by things like taxes and range loss or mortgage or window attenuation. At the end, you have so much money and so much energy left over, and that's all that's available for the rainy or foggy day, as the case may be. For each of our systems, in this case the Elliptica and GigaLink parabola unit, we can calculate a link margin curve versus range, as shown here. This shows that for the Elliptica, at a range of 1 kilometer, you have right around 35 dB of available margin. And going back to our earlier discussion, that's, 3 factors of 10, and about a little over, not quite 2 factors of 2. So you're talking right around 2,000, almost a factor of 4,000 available margin on a clear day at a range of 1,000 meters. The parabolic unit, or millimeter wave unit, at that same range of 1,000 meters only has about 10 dB of margin, which means it only has about 1 factor of 10 available before it will suffer outages or errors due to attenuation. The next step in determining how link availability can be calculated is understanding what the weather attenuation will be over time. This particular graph shows the attenuation of fog for optical frequencies in 3 cities of Phoenix, Denver, and Seattle for various probabilities. as you can see that a city like Phoenix, which almost never gets fog, the probability of having 100 dB per kilometer attenuation is about 99.975 probability of occurring. That's just not very likely to get a 100 dB per kilometer event. That being said, in Seattle, that same probability is about 99.915, which is actually considerably more common and implies that you're going to see it for 6 or 7 hours a year. Based upon that, we can deploy an FSO system at much longer ranges in Phoenix for the same availability that we can in Seattle. Denver is shown as a city a bit in the middle, where the average attenuation is not as good as Phoenix, but quite a bit better than Seattle. Typically, these curves are calculated from visibility information that is gathered at airports around the world. This information is gathered on a 1-hour basis, and there are many databases extending back 17 to 30 years with this information. The only limitation to that is even over 17 years, once-an-hour information really is not enough to extrapolate how much attenuation will occur at a 5-9s event. I mean, 10 years is the equivalent of about 80,000 hours, and a 5-9s event is 1 part in 10,000, so that means over 10 years you'd only get 8 data points. That's not enough to make a good statistical example, and that's why for worst-case FSO performance, we tend to look at the worst-case fogs recorded on the planet and use that to predict range. In addition to the fog attenuation, it is necessary to take into account the prevalence of low clouds. And what that means is that these curves also have an altitude factor. In Seattle, for instance, fog at ground level does occur, but not as frequently as low clouds will envelop the top of the tall buildings. And using just the visibility information from airports is not enough. It is necessary to incorporate the cloud statistics into it as well. A third factor that also should be looked at is the prevalence of the urban heat island. And what this means is that humanity generates heat, which tends to push fog away. And if you're using weather statistics from the airport, which may be far from the urban center, the statistical probability of fog will be different. From a typical installer or user standpoint, you really don't have to worry about this. Terabeam provides the information. We will calculate these availabilities for you. But it is important you understand what drives them in looking at an installation, and that when predicting performance, it will be more accurate at an airport and slightly less accurate as you get further away from those locations. Millimeter wave availability is actually substantially easier to predict, and that's because it's based upon rain rate. And there are excellent models that mathematically determine the probability of rain for the various regions on the Earth. Whether they be the Crane region models as shown on this slide, or the ITU rain region models, it's relatively easy to determine what statistical probability of a given rain event is. By looking at the clear air link margin and then the probability of a given weather event, it is possible to predict or determine at what range a system should be deployed for a given availability. This chart shows for elliptica FSO and gigalink millimeter wave at 3.9s what the performance will be in various cities. In Las Vegas and Phoenix, which are two really great FSO cities where fog is quite rare, the 3.9s FSO performance is beyond 4,000 meters, whereas millimeter wave is limited to about 1,250 meters due to oxygen absorption. So really, weather just isn't a factor in those two cities. If you go a little further to the right and look at a city such as Atlanta, which has both rain and fog, the millimeter wave system is limited to about 1,000 meters at 3.9s of availability, whereas the FSO system is about 450 meters in that same city. So once again, it's very important to understand where a system is being deployed because its range will depend greatly on where that location is. The next topic here is safety. We believe that safety is one of the most important things that we can build into a product as a manufacturer. In addition, Terabeam's experience as an operator has forced us to truly understand these safety standards and to be very conscientious of how they affect the user or the carrier organizations deploying these products. Around the world, there are 3 laser standard safety organizations. The first in the United States is the Center of Devices and Radiological Health, which is a division of the FDA. And it establishes standards for product safety, labeling, and installation. Also in the United States is the American National Standards Institute, which establishes user safety standards, and that is distinctly different from product safety standards. In general, the ANSI regulations have the power of law because they're recognized by OSHA. And they are slightly different from the CDRH recommendations when you compare them at the fine levels, but they both need to be taken into account. Internationally, the primary body is the International Electrotechnical Commission, or IEC. This group is used in most of Europe, certainly the CE mark. Japan, in particular, uses a version of IEC, and there's a fair amount of commonality around the world based upon IEC standards. The US is actually one of the unique ones out there that hasn't quite homologated itself with the rest of the world. One day, we're hopeful everybody will be the same, but it isn't yet. When you look at the 3 laser safety organizations and how they actually classify systems, they tend to be very similar. All of them have Class 1 through Class 4 definitions. Unfortunately, some of them are Roman numerals and some of them are Arabic numerals, and some of them use A's and B's where the other uses M and R's. And the result of this is, as a manufacturer of the products, it's necessary for us to take into account the least common denominator when classifying our products. Or we have to label them slightly differently for the various regions in which they're sold. In general, the CDRH is the most conservative body and has the most conservative rules. That being said, the CDRH has recently issued a memo allowing us to use the IEC standards in a preliminary basis until they actually change their rules. This is unique and a bit confusing, but once again is something that we take care of, not you, the installer. Typically, we like to install systems that are true Class 1 for all 3 organizations. And what this means is that a Class 1 system, whether it be CDRH, ANSI, or IEC, is eye-safe under all conditions. And all includes the use of binoculars right in front of the system. Most other FSO systems sold around the world are really defined by the IEC Class 1M standard. And 1M means the system is safe to the naked eye, but may not be safe in the presence of binoculars. And for a user organization, the way this manifests itself is that if installing a system in an area where binoculars could or may be used, it is necessary to put up signs warning that they should not be used. In our experience, that is a particular barrier to acceptance from the carriers, in that they do not want to put signs up saying, don't use binoculars here. Whereas with a Class 1 system, which Elliptica is, no warning signs and no labels of any kind are required. As you look further down this chart, you will see Class 2 and Class 3 systems, and even Class 4. Class 2 does not apply to FSO systems in general because it is typically a visible wavelength only standard, and FSO systems very rarely operate at those frequencies. Class 3 systems, there are a few FSO systems available on the market today that operate at those power levels. Those systems are not safe to the naked eye and should be installed only in conditions appropriate for that. Class 4 systems can actually be quite hazardous and are capable of introducing actual burns if someone gets in front of the system. To my knowledge, there is no Class 4 FSO system anywhere in the world today, and I doubt you will ever see one in the commercial space. A core part of all the safety standards for FSO use is defining exactly where a given system can be used. And at present, the regulations defining this are still under evolution, but the IEC organization is in the presence of finalizing a document that will fully define the appropriate installation requirements. To first order, a Class 1 system can be installed anywhere, completely unrestricted, whether it be the office environment, the school environment, rooftop, or even on the street. It is completely safe anywhere. A Class 1M system should only be installed in a restricted environment. And a restricted area is defined as a location where only personnel with a knowledge of the area will have access, behind locked doors, or in areas where the general public cannot have access. And that includes areas such as on the outside of a building where a window washer would be. That is considered a restricted environment, and a Class 1M system may be installed there. Class 3B and above systems should only be installed in controlled environments. And those are areas where only trained personnel can get to, and that if the system is intercepted within that, or if someone blocks the system within that area, the system should power down automatically. Once again, these are all safety requirements and are designed to protect both the public and the users from the systems. From a Terabeam perspective, we are only building Class 1 FSO systems, so the rest of these restrictions really don't apply. But the differences between Class 1M and 3B can be particularly strong selling points when compared to other products. The core factor in governing eye safety is the response of the human eye to light. In general, the concern is how effectively will the human eye focus that energy and possibly cause injury to itself. For wavelengths above 1400 nanometers, energy will be stopped almost completely at the corneal tissues. At wavelengths less than 1400, the energy will pass through the cornea and will be focused by the optical system that is the eye to some extent. As you get closer to visible, that amount of focusing will get tighter and more potentially dangerous depending upon how much energy is entering the eye. From an overall comparison standpoint, an FSO system at 1550 nanometers can transmit 50 to 65 times as much power than a 785 or 850 nanometer system for the same eye safety classification. And once again, that is an important selling differential and is why a 1550 system like the Elliptica can be a true Class 1 system, whereas most other systems on the market today are Class 1M. That being said, I would like to state that it is very possible to build safe systems at all wavelengths, and that it is also possible to build Class 1 systems at all wavelengths. It is part of the engineering challenge and should not be considered an absolute safety factor, but a design decision. Well, that represents the end of this presentation. I hope it was informative, and if you have any questions, I'm sure representatives from Terabeam can help you at any time. Thank you.